Hello and welcome to Sean White's Solar and Energy Storage Podcast. The title of this podcast is Energy Storage Technology Comparisons, including solid oxide fuel cells, lithium-ion versus lead-acid, sodium-sulfur batteries, and UL 9540 and UL 1973. In this podcast, we will cover solid oxide fuel cells, Bloom Energy, the Bloom Box, hydrogen from natural gas production, server modules, ethanol, lithium versus lead acid, the solar family reunion, nameplate capacity versus usable capacity, round trip efficiency, Cobalt, the Graphite Anode, NMC, LFP, LifePo, NCA, Reactive Power, otherwise known as Q, Black Start, VRLA, that's valve regulated lead acid, AGM, nickel metal hydride, silicon graphite anode, Tesla batteries, sodium sulfur, UL 9540, UL 1973, LG, and more. To learn more about energy storage, go to solarsean.com. We're going to cover a number of things, and we are starting off with solid oxide fuel cells and then going over different battery technologies. Some of this may be review, but I think it's very important to remember what we've been studying. So study up. So let's talk about a fuel cell that is not a hydrogen fuel cell. It's called a solid oxide fuel cell. So it takes hydrocarbons rather than just hydrogen. So that's hydrogen with carbon. There's a company that's kind of popular that has pioneered these solid oxide fuel cells. They were big in the news a while back, and they typically take natural gas. This is called Bloom Energy. In fact, it's in Silicon Valley where I am, and if I wanted to, I could even walk there. It might burn about 500 calories. It would be a good walk, but I could do it. And calories, yes, I'm always talking about energy. And so Bloom Energy is a high-tech company. A solid oxide fuel cell, that's from AVL. So they're talking about 35 to 50% efficiency. And you also have to remember that most hydrogen is not made from renewable energy. You can make hydrogen from renewable energy, but it is usually made from things like natural gas because it's cheaper that way. It takes liquid or gaseous hydrocarbons. It directly oxidizes the fuel. And the benefit is that it is cleaner than explosions. That's right, combustion for an internal combustion engine. And you don't have to replace spark plugs. But hey, with fuel injection, you don't have to do that anyway, huh? Some of the different components of the solid oxide fuel cell. Some people have called this a Bloom box. I remember when it first came out, it was like this magic box that made electricity from natural gas without burning things. So the fuel cell, that's typically about 1 volt, then we stack those things up into a stack. Then we will call it a server module. Yes, server, that's right. You can tell that we're in Silicon Valley. A bunch of server modules will make a server, and then a bunch of servers can make a power solution, and we can put that into a 30-foot shipping container. So kind of funny, you just hook up your natural gas pipeline and you get electricity. You can do that with a Generac generator too. But this one is a little bit cleaner. A possible car with a solid oxide fuel cell. You don't hear too much about these, but they are calling it the biofuel cell. So they're using biofuels. Typically, we're talking about the biofuel being ethanol. So ethanol is typically made from cracking corn. That's right, fermentation. You ever heard of that song, Jimmy Crack Corn? And I don't care, Jimmy Crack Corn, and I don't care. That is about making whiskey. I actually learned that in my college history class. So they go down there to Brazil, perhaps. They're famous for making ethanol. So they're taking CO2 out of the air to make that ethanol. And then they put that CO2 back into the air after they put it through the solid oxide fuel cell. So we can consider that renewable energy. Now, personally, what I would have to look at there is that it is green, but it takes a lot of diesel to grow corn, typically, with tractors and all. And photovoltaics are more efficient than photosynthesis. So that perhaps is why this technology hasn't taken off like crazy. But hey, theoretically, I guess you could stick whiskey in your gas tank. Now, don't go buying whiskey now. Might hurt your liver. So just some statistics from a U.S. national lab, Pacific Northwest Laboratories. And they're saying that natural gas fuel cells have 33% less upfront costs than a natural gas power plant and create 15% less carbon dioxide. You know how to make less carbon dioxide? Quit breathing. So that's it for our fuel cells. Let's just talk about some interesting things from Clean Technia. And we are always looking at getting to be less than $100 per kilowatt hour. And there's been some articles in the past speculating that Tesla battery cells cost less than $100 per kilowatt hour to make. And that's just for the battery cells. So perhaps, according to this article, that the battery packs are already $100 per kilowatt hour. And perhaps that's why Tesla stock likes to be going up all the time. Some lithium versus lead acid arguments. You always hear, especially the old timers, trying to take the lead acid side. In fact, there's something called the Solar Family Reunion, and they've been having some parties in the solar industry, lots of old timers there. And when it was coronavirus, they started doing some online meetings, and they would have different discussions where you could go into different rooms. And one of the topics that was popular was lithium versus lead acid. So one of the things that we want to look at that makes a big difference is the nameplate capacity versus the usable capacity. So how far are you going to cycle your battery up and down? Lithium typically has more usable capacity. So if you're saying that my battery is so many kilowatt hours, with a lead acid battery, if you want it to last for a long time, typically you're going to only use 50% of those kilowatt hours because it's bad for your battery to drain it all the way. Worse so for lead acid. For lithium batteries, we don't want to fully charge and discharge them either. And it depends on who you're talking to, how deeply you're going to cycle these batteries. There's some technologies that you can cycle them up and down all the way. So we were talking about capacitors, pumped hydroelectric, flywheels. Doesn't hurt them at all to have them completely discharged. So some other things that we were going to compare to, besides the depth of discharge, which has to do with the usable capacity, that's how far you can discharge it, is the efficiency. So I think that's very important, the round trip efficiency of the energy storage system. And we're talking lead acid. A lot of times we use the number 0.7 or 70% for our derating there. And lithium oftentimes is up in the 90%. So that would mean 10% loss versus 30% loss. So that's triple the losses for lead acid. Lead acid does beat lithium for cold temperatures though. So 50% depth of discharge, that's for lead acid. And oftentimes for lithium, we can do an 80% depth of discharge. There is a 100% state of charge, so that's a fully charged battery. That's a 0% depth of discharge. Now at 20% state of charge, that means we've drained 80% of our battery. This would be not too good for the longevity of a lead acid battery. So you don't want to do this with a lead acid battery. A 65% state of charge, so we've discharged it 35%. And not good for any battery, especially lead acid, which is a 0% state of charge, total dead battery, like leaving your lights on overnight. And that is 100% depth of discharge. Another thing I like to point out is with lithium batteries, it's not as good for the longevity to top them off. So 100% state of charge is typically not as good for a lithium battery for longevity, but 100% state of charge is great for lead acid battery. And with a lithium battery, you can do 100% state of charge, but if you do it every day, your battery is not going to last as long. So they say if you have an electric vehicle, you might already know this, that on a regular day, when you're not going on a long road trip, you don't do 100% state of charge. But you can, so they're not against it. So it's not terrible, but it's just not good to have 100% state of charge. This is one of the reasons why we don't put 4 lithium iron phosphate batteries in series, which adds up to 12.8 volts, and stick that in our car, which would work, but we'd be at 100% state of charge all the time. And that's not good for that LFP, that lithium iron phosphate battery, to be at 100% state of charge all the time. But with lead acid batteries, your car battery is typically always at 100% state of charge. Okay, back to lithium. Remember cobalt, that's the CO, cobalt. We're not talking carbon monoxide, that CO. We're talking about the periodic table of CO for cobalt. It's great for lithium batteries. And that's what they're putting in cars for the most part. But it comes from the Congo. Sometimes they use slave labor and child labor, and that's not good. And they could be happier going to college. Cobalt has a trend of going up in price, obviously. And something that's interesting, they're trying to figure out how to get a clean supply of cobalt. You might have seen that Blood Diamond movie with Leonardo DiCaprio about how cruel it is. Some of these industries mining for things like diamonds and perhaps cobalt in Africa. So they're trying to use blockchain, that's the distributed ledger technology, to figure out where all the cobalt comes from. So you can identify where the cobalt has been coming from that you're using with a distributed ledger blockchain technology. And we're just going to go over the top 3 battery chemistries. And so we find these chemistries in the cathode. Typically, we're going to have a graphite anode with our mainstream lithium-ion batteries. So that's a graphite anode. Anode's the negative side, and the cathode is the positive. And what do we have in the cathode? First of all, we have NMC. What does that stand for? That's lithium, nickel, manganese, cobalt, oxide. Now, the next one that we have, let's call it LFP. What does that stand for? That's right, lithium iron phosphate, also known as LifePo. And then the last but not the least, because it has the greatest specific energy of this group, is NCA. And what does that stand for? That's right, lithium, nickel, cobalt, aluminum oxide. So this is all subject to change, but Tesla, they're popular in the news, so we're going to talk about them a lot. Their cars typically are using NCA. Utility storage can also use NMC. In their future cars, possibly NMC, and we also have had announcements about LFP in China using the cattle batteries. Another acronym for you, LIB for lithium iron battery, and we can see sometimes people call it NCM versus NMC, same thing, just a different arrangement of letters, but we do have to be careful there. And one of the things, remember the C, that's the cobalt, that's the expensive thing. That's the thing from the C from the Congo, and we want that to be less. Lithium iron phosphate, which has less specific energy, but it has less cobalt, and it's very rugged. It's better at handling things like overcharges and heat, stuff like that. Back in 2018, if Tesla is going to do 0% cobalt, that means they're changing their chemistry. We'll see if and when that happens. So right now what we're going to do is we're going to reiterate some differences that we have with lithium versus lithium, different types, and lithium versus, say, for instance, lead acid. So with lithium versus lead acid, you can cycle it down much further. So you can go to a greater depth of discharge, less state of charge. With lithium batteries, connecting in parallel is not a problem. With lead acid batteries, parallel connections are to be avoided. You can do parallel connections with lead acid batteries, but things do not work as well with parallel connections with lead acid batteries. And now lithium iron phosphate versus lithium with cobalt is with lithium iron phosphate, thermal monitoring, that's for temperature, is not required. So you don't need little thermostats on your battery cells. But with cobalt, yes, you do need to have thermal monitoring within your BMS. And what is BMS? That's right, battery management system. All lithium batteries are going to have a BMS. Or at least I should say all good lithium batteries. And then another thing for lithium is it's maintenance free. You're not going to be going in there and adding electrolyte, for instance. One of the things interesting about fire protection, I was doing some work with a big company, and one of the things that they'll do is if there is a fire, they can take all the oxygen out of a container by having some pressurized non-oxygen gas inside of there. So the benefit is it can put out a fire, but the drawback is that gas can build up, and then in some cases, you could have such a buildup of gas when it finally does reach some oxygen, it can create an explosion. So it is controversial whether you should suppress the oxygen inside of a container or not. Also, if a firefighter went in there without oxygen, or somebody else that's not a firefighter going, what's wrong? They could pass out because they couldn't breathe. So it might be dangerous to go into a battery container if there's a problem. Another thing, if there is a fire, that they could put an attachment on one of the containers where you can attach it to a fire hose. And when you figure all your equipment's going to get wrecked anyway, you just flood it. So lithium does react with water and explodes, but the lithium-ion battery does not have that problem because there's very little lithium in the lithium-ion battery. It's not like it's a solid piece of lithium metal. So Q, and that's reactive power. And so we're not going to completely have everyone understand reactive power, but we can just say what it kind of does. And it helps regulate the voltage, so it stabilizes the voltage. Injecting reactive power into a system raises the voltage. Absorbing reactive power lowers the voltage. And if there's lots of load on the lines, the transmission lines absorb the reactive power and lower the voltages so we can add reactive power to stabilize those voltages. That's what reactive power is without going into the physics of it. And we symbolize it with Q. And if you're a Star Trek fan, the omnipotent Q. So that's also your homework. Go look out for Q. He's actually on the first and last episode of Star Trek: The Next Generation. So we get reactive power when current leads voltage. So current and voltage can go out of phase with each other. If current lags voltage, we get a lagging power factor. So reactive power is produced when current leads voltage. So we talk about leading power factor where current is leading the voltage. So it's like we have current and voltage out of phase with each other. Isn't that crazy? You can have positive current and negative voltage at the same time, and that is called reactive power. And then if we switch it back and we have current lagging voltage, we can call that lagging power factor. And if we don't have enough reactive power, our voltage can collapse. We can get blackouts. And that's why with larger inverters, we want them to make reactive power. When inverters are just a small part of the grid, like when solar was new, we didn't need to make that reactive power. It just wasn't a big enough part of the grid. But as renewable energy increases, there are requirements. In fact, there are new requirements. In fact, if you're in California, they have something called Rule 21 where they have to use UL 1741 SA inverters that can make reactive power. And that would be for our interactive inverters, whether it be for energy storage or solar or whatever. So there's lots of different types of ancillary services that your energy storage system can do. And one of the things that we can do is frequency regulation. And sometimes frequency regulation can be called droop control, and you can change the frequency by adjusting the output of the power. So if the frequency goes down, you step on the gas, you add more power. If the frequency is too high, you take away some power and you fill up your battery. And so that could be also called droop control. Okay, so here's some energy storage criteria. Energy density, energy per volume. Specific energy, energy per weight. Round trip efficiency, that means you got to take into consideration charging and discharging. Some other important things that you want to look into with energy storage is what is the lifespan of your technology? How long is it going to last? And that might have to do with the depth of discharge. Because if you discharge something faster or you do something when the battery's hotter, lots of different reasons why you're going to shorten your lifespan. And just in general, hot temperatures make electronic equipment not work as well. Even that device that you're watching video on, when it gets hot, it doesn't last as long. Black start generator, and big power plants will have this. So if the electricity goes totally 100% down on the grid, what they have to do is to get something to start it up, to get that frequency going. It's interesting that generators naturally sync with each other when they're on the grid, but we have to get that first thing out there for everything else to sync with. An energy storage system can replace a black start generator on the grid, but it's typically done with a diesel generator. And so they'll have these generators just sitting there all the time, not doing anything because the grid usually doesn't go down. And then when it goes down, it's got to be ready to roll and make some sine waves so the rest of the grid could start up and sync with that. So that's called a black start. You'll be hearing about that with different battery and inverter companies saying how their systems will do black start. So just some different terminology that we have. We have an energy management system. We have a battery system that might include a BMS, battery management system. We have a PCS, power conversion system. The National Electrical Code, we will call an inverter a type of a power conversion system. Then some of the things that go into the battery rack is we have a battery cell, battery module, there's a battery management system, junction box, and a lot of times you stick them on a battery rack and put a bunch of these racks inside of a container. Container is a nice way to put something indoors that's sitting outside. But then if something catches fire, it's just a container instead of a building. So many professionals don't recommend putting the batteries inside of buildings. Some advantages and disadvantages of lead acid batteries, low cost and simple manufacture, but the cost of lithium is very competitive, especially when you take things like depth of discharge and round trip efficiency into consideration. But it is have a simple manufacturing process and it's been around for a long time. So the cost is a little bit debatable now when we're comparing to other technologies. It has high specific power. so it can discharge at great currents, like your starter motor of your car. It works better than lithium batteries as far as high and low temperatures go, and we do not need a battery management system. So that's like a little mini computer to tell it what to do. But it's got a low specific energy, so that means it weighs a lot for how much energy you get. And even though you can discharge it fast, it takes a long time to charge it. If you don't fully charge, often you can get sulfation, which reduces the life cycle of the battery. With flooded lead acid batteries, you oftentimes are going to be doing maintenance, which means adding water, doing an equalization charge, and lead is bad for you. Different types of lead acid batteries. We have the sealed or maintenance-free battery. Sounds good if you don't have to do maintenance, but then perhaps you can't make it last as long because you can't add distilled water to it, and so it won't last as long. A starter battery, also called a SLI or starting, lighting, and ignition, is made to be fully charged all the time, and then you take a bunch of current out of it for a second to start your car. Otherwise, you're not cycling that battery down. So it has a lot of surface area, lots of thin plates. Deep cycle battery has less surface area but thicker plates, and that is made for cycling up and down. Deep cycle batteries can last up to 15 years. SLA, or sealed lead acid battery, and so that's something it's sealed, so you can't add fluids to it. We have valve regulated lead acid, which can also be sealed, and absorbent glass mat, or AGM, which also they can call maintenance free. Now, nickel cadmium batteries are just not popular anymore. Lithium has kind of taken over. Unless perhaps you're on an airplane. The aircraft industry is afraid of lithium batteries blowing up sometimes, and will sometimes still use NiCad batteries, but we just don't see NiCads being used very much anymore. But if you had some old NiCads laying around, be careful, they're toxic. And then also, along with NiCad batteries goes nickel metal hydride. They have gone extinct. That's also known as the way of the dodo bird. That's an extinct bird. I do have nickel metal hydride batteries because I have a classic hybrid car. And they weigh about double of what a lithium-ion battery is for the same weight, and we're just not going to be using those anymore. Now, lithium-ion, so we can have lots of energy per weight, that specific energy. Can put big loads on them. They last for a long time. They can sit on the shelf without getting wrecked for long periods of time. Low internal resistance, reasonably short charging times. That can be very important. Some of the drawbacks for lithium-ion is we need that battery management system to prevent thermal runaway. It's a protection circuit. High temperatures are not good for it, so we oftentimes have cooling going on, liquid and air-cooled batteries. We're not going to rapid charge when we get down to freezing, so we might need heaters with our batteries, so heaters and coolers, and they're difficult to carry on the airplanes in large quantities. Some different stages of how Tesla has been developing their batteries. They had stage one, which was 2009 to 2012. That was the Tesla Roadster. I got to test drive one of those in the Model S. Stage 2 was the Model S and the Model X, and then stage 3 was the Model 3. Tesla has often been working with Panasonic and others. So the stage 1 batteries were the 18 by 65 millimeters, the 18650s, and they required 11 kilograms of cobalt per car. No silicon on the anode. That was also the NCA formulation. Okay, so stage 2, they were still using 18650s, but instead of 11 kilograms, they only need 7 kilograms of cobalt per car, and they put a little small amount of silicon in the anode. Silicon on the graphite anode makes the battery more energy dense. However, silicon expands. So the trick is how much silicon can you put on the anode before things expand and relax and start breaking things, because expansion is not good. And they're working on new technologies for that. And I don't mean Tesla, but other people too, at fancy universities. And we will see where that takes us. But perhaps in the future, they will figure out how to compensate for that expansion and contraction of the silicon on the graphite anode. The Tesla battery, it goes on the bottom of the car. Good for a low center of gravity, good for handling. And now we're talking stage 3, that's the Model 3. And so we've gone from 11 kilograms to 7 kilograms to 4.5 kilograms of cobalt per vehicle. And they're using the silicon graphite anode, which is probably higher in silicon than their stage 2. And at the time that I got this information, it was powering all the Teslas and home energy storage systems. As far as we know too, there's a lot of secret stuff going on with these big corporations. Just want to mention that General Motors has been using LG for their batteries. It's a little sodium sulfur battery review. We see that at some large power plants, especially in the past, but lithium-ion has been beating sodium-sulfur, and I think it's just because of the mass production of lithium batteries for cars has brought the price down, and so it has kicked sodium-sulfur out of the market for a good part. Good energy density, around 90%, long cycle life, and instead of having to keep the temperature low, you can have a very hot temperature. In fact, you have to heat it up. Perhaps you can use waste heat to heat these batteries if you have them in a place where there is a lot of heat, and that would be 300 to 350 degrees Celsius. So some of the advantages: inexpensive sodium and sulfur. It can last for a long time. Good energy and power density. Good charging, discharging, great efficiency. Doesn't matter if you have hot ambient temperatures. In fact, that can help. The disadvantage, though, also has to do with temperature. You have to get it up to 300 degrees. Sodium also can explode when exposed to water. One of those chemistry experiments that can be exciting. So you have to make an enclosure that will prevent leakage. So we could see some more sodium sulfur out there, but we will see. Let's take a peek at some of the different UL, that's Underwriter Laboratory listings, for a Powerwall, for instance, but we'll see this on a lot of Powerwall competitors. There's UL 9540, and that's the standard for energy storage systems and equipment. Then there is the UL 1642, which is a standard for lithium batteries. And we have the UL 1741, that's for the inverters. We also have that for even solar inverters. And we have the UL 1973, that's the big one that we're usually looking at and looking for here. And that's standard for batteries used in stationary, vehicle auxiliary, power, and light electric rail applications. So it can be used for these different applications, but we're just picking the stationary for us here. So it doesn't mean that we're going to also be driving a train with it for our light rail, but stationary applications in UL 1973, that's oftentimes what we're looking for. LG home battery was just listed to 1642 in 1973, and many are just to 1973, and so that's what perhaps your electrical inspector would be looking for, was that 1973. So I hope you enjoyed this. Put that in your memory banks. Thanks for listening to Sean White's Solar and Energy Storage Podcast. To learn more about storage, go to solarsean.com. We've got classes, we've got books, we have everything